Hello and welcome. This is going to be our lecture video for March 3rd through 4th. Let's go ahead and get started with this warm-up. Write the equation of a rational function with the following features. I want vertical asymptotes at -4, 5, and 6, a whole at 2, and horizontal asymptote at y equals 3. Let's think about how we could do this. So there's not going to be one right answer, but there's definitely some things our equation needs to contain. So we'll start with the y equals. And we know it's going to be a rational function, so I'll make a really long fraction line because I see I've got a lot of features. I'm going to have to put a lot of different things in here. Okay, so first thing, vertical asymptotes at -4, 5, and 6. To cause those in our graph, I need to put in the factors x plus 4, x minus 5, and x minus 6 into the bottom of our fraction. So that is, we divide by numbers close to -4, or when we plug in numbers close to -4, 5, and 6, we'll be dividing by a number very close to 0. And that's what is going to cause our function to spike up to infinity or down to -infinity. All right, there needs to be a hole in this function at 2. So I'll put in the factor x minus 2 into the bottom, but I'll cancel it out by putting that same factor on top. So now at the value 2, this will become 0, but it won't spike off to infinity because this is becoming 0 at the same rate. So these cancel out, and then right at 2, I have 0 over 0. Sorry. And that's going to be a hole in our function. All right, in order to get a horizontal asymptote at anything other than 0, I need the degrees on the top and the bottom to match. So I need to put in 3 more factors on top. So I could do maybe like an x plus 1, x plus 2, and x plus 3, being careful not to accidentally match one of these because then I would get rid of one of my vertical asymptotes and trade it out for a whole. All right, so now that the degree of the top and the bottom match, the horizontal asymptote will occur at the ratio of the leading coefficients. We can control what that's going to be by just putting a 3 and a 1 in front of both of these. Don't necessarily have to write the 1, but there now it's clear that after we distribute all of these, if we then distribute in a 3 and a 1, the 3 and the 1 will become our leading coefficients. 3 over 1 is 3, and so now we've got our horizontal asymptote where we want it. All right, warm up part 2. Here we've got a function, a rational function in factored form, and I want to sketch a graph of this. So first off, let's notice that the x minus 2's will cancel out. So that's going to cause a hole at x equals 2. The x plus 4 doesn't cancel out, so at -4, the value that will make this equal to 0, I expect to see a vertical asymptote. The factors left on top will cause x-intercepts. We'll have an x-intercept at -5 and at x equals -3. All right, now what type of end behavior do we expect? Also, we can investigate the y-intercept by expanding this out, or well, distributing this, and then taking a look at the standard form. So I'll distribute what I've got right now, x squared plus 5x plus 3x becomes an 8x plus 15. And I don't think we need to bring in that x minus 2. I had to think about that for a second, but I'm pretty sure we can just do the long division right now with just the x plus 4 and not include these. All right, so x times what becomes x squared, x times x becomes x squared. So I get an x squared plus 4x when I distribute this back in. Subtract that away, and I'll get 4x plus 15. X times what becomes a 4x, x times 4, and then we can stop here because we have our linear equation. It's just y equals x plus 4. All right. Now, this was our expression on top. This was on bottom. We can figure out our y-intercept by, first I'll write it out like this. And then all of these terms would cancel at the y-intercept because x is equal to 0 at the y-intercept. So they don't really cancel, they just become 0. And we're left with a y-intercept of 15 over 4. Okay, so let's put all of this together into a graph. Start with coordinate plane. We'll approximate the line y equals x plus 4 is our slant asymptote, so it's going to look a bit like that. We'll just label it as y equals x plus 4. It's going to cross right there at 4. Because it's got a slope of 1, this is going to cross at -4. We said we would have a vertical asymptote at -4, so right where that line is crossing, we'll have a vertical line. Just like that. That's our vertical asymptote. X equals -4. We said we'd have x-intercepts at -5 and -3, so either side of this, -5, -3. We said our y-intercept would be 15 over 4. That's just a little bit under 4, so very close to this point here, but it's 3.75 as our y-intercept. All right, now in order to hit these points, I must be on this side of that slant asymptote, hit that point, and then go up over this wall, up to positive infinity, disappear, reappear at negative infinity, come in, hit these 2 points, and then as it moves off this way, it's just approaching that slant asymptote. Okay, there's one more feature that's easy to forget, and that's that there was a hole at x equals 2. So we're going to go to x equals 2, go straight up to our function, erase a little spot, put a hole in there right above 2. If we wanted to know the elevation of that hole, we could plug 2 into this form to see where that line is continuous through. Let's see, we get 4 plus 16 plus 15, that's 35 divided by 6. So 35 over 6 is just a little bit under 6, so it's about equal to 6, which is about what that looks like. So I think we've done a pretty good job sketching this. Okay. Goal for today is to review graphing rationals and to multiply, divide, add, and subtract rational expressions. While we do this, you must combine two fractions into one before you can solve an equation. All right, so here's my note at the beginning. If you can multiply, divide, add, and subtract numerical fractions, I should have said numerical fraction, then you can do the same with rational functions. It just takes a little longer and always factor first. So let's review. How do we multiply two fractions? Well, you might say, okay, just multiply straight across and straight across the bottom, but we want to get really good at cross-simplifying with our rational expressions, so let's do that here. 10 and 15 both can be divided by 5, so this can become a 3 and a 2. So that's called cross-simplifying, and now when I multiply, if you cross-simplify correctly, you'll never have to simplify your final answer over here. All right. Well, except for this can be simplified, and that's because I didn't cross-simplify or then re-simplify after I cross-simplified. 3 divided by 3, that just cancels out, and I'm just left with 2 over 7. All right, and that can't be simplified. All right, now how do we multiply two rational expressions? Well, that note at the beginning said always factor first, so let's factor this x squared minus 1. Anytime, this is just a good one to memorize, how to factor x squared minus 1. You know, 1 is a perfect square, but we often forget that one. Just remember x squared minus 1 factors into x plus 1, x minus 1. That way we get our x squared back, we get a plus x minus x, those cancel out, and then the last terms give us that minus 1. All over 7. And the reason we did this is now we can cross simplify and cross out an x plus 1. All right, then just go ahead and distribute that 2 in. And I'm left with 2x minus 2 all over 7. All right, distribute on the top. We're going to leave the bottom factored, but the bottom is only a 7 here, but in the future, leave the bottom factored. Okay, the instructions might not explicitly say to multiply, but if it says simplify and we've got multiplication, we're going to use the same technique. Take a second, maybe pause the video, copy this one down. Now we need to practice factoring this. So I like to set up my factors first, and then in my head I ask the question, what two numbers multiply to be negative 6 but add to be positive 1? That's going to be plus 3 and minus 2. And then I double check by just sort of quickly foiling it in your head. All right, over here, this is that same setup with reciprocals. 25 is a perfect square, so I can do x plus 5, x minus 5. And that will give me x squared minus 25 back. And on the bottom here, set it up, and then two numbers multiply to be 3 but add to be 4 are 3 and 1. Now look to cross simplify, and x plus 3 can cancel out, and x minus 5 can cancel out. And then with the remaining factors, I will go ahead and FOIL those first, outside, inside, last. And I get an x squared plus 5x minus 2x becomes a plus 3x minus 10 all over x plus 1. And again, that rule of distribute the top but leave the bottom alone doesn't apply here either, because the bottom is just a single factor, but we wouldn't distribute on the bottom anyway. Let's change the color on that. All right, how do we divide two fractions? Well, you've probably learned copy, dot, flop before, and that's going to work for our rational expressions as well. So 2 over 5, the division becomes multiplication. Flop this and becomes 9 over 4. Before we actually multiply, we look to cross simplify. The 2 and the 4 can both be divided by 2, turning this into a 1 and a 2. 1 times 9 is 9. 5 times 2 is 10. We're left with 9 over 10. All right, let's do the same with some rational expressions. Copy, replace with multiplication, flop. I see I can divide this 2 and this 4 by 2, turn this into a 1, this 4 into a 2. All right, and then I'll want to write this in alphabetical order with the coefficient in front. So 2yz all over, and then x times x, we'll rewrite that as x squared. And now that's fully simplified. All right, how do we add two fractions? Well, the main idea is get a common denominator, then add the tops. One thing that will always work to get a common denominator is multiply the two bottoms by each other. So 3 times 8, 8 times 3, those are both 24. But whatever I do to the bottom, I must do to the top. So if I'm multiplying the bottom of this by 8, I multiply the top of this by 8. Multiplying the bottom of this by 3, top of this by 3. And now I've got 8 over 24 plus 21 over 24. Add this together and we get 29 over 24. And we'll just leave our answer like that. There's no mixed number equivalent for a rational function anyway. So, all right, how am I going to add these? Well, I could multiply the bottoms by each other, but I'll end up with some really big polynomials. I don't want that, and I want the bottom to be factored in the end anyway, so let's go ahead and factor first. X over x minus 1, that can't really be changed, but I'm going to leave a little bit of space next to it in case I want to add more to the top and the bottom. 2x minus 1, no common factors there, but on the bottom here we can turn this into, let's see, two numbers that multiply to be 2 but add to be negative 3 are going to be negative 2 and negative 1. All right, and now what I might recognize is that the bottoms have something in common. I don't have to multiply them by each other because they both already have an x minus 1. So I don't want to add in another x minus 1 to either of these when they already have that. What I do want to do is add in an x minus 2 to this denominator, and now they actually do match. They both have an x minus 1 and x minus 2. Might go in different orders, but it doesn't matter. And whatever I do to the bottom, I do to the top. Extend this fraction line a little bit. And now that the bottoms match, we can add the tops. And I sometimes do this before doing any sort of distribution. So x times x minus 2 plus 2x minus 1 all over, and then I only need one copy of this. Maybe I'll go with the one that's in more numeric order, x minus 2, x minus 1. All right, and then on the top, we just combine everything. So distribute in this x, I get x squared minus 2x plus 2x minus 1. These cancel, and I'm left with x squared minus 1 over x plus minus 2, x minus 1. And occasionally, this setup might lead to something on the top that can then be factored, and maybe even some more canceling can happen. So x squared minus 1, this is the one I asked you to memorize, is x plus 1 times x minus 1. On the bottom, we still have an x minus 2, x minus 1, and these can cancel. And that whole thing simplifies down to just x plus 1 over x minus 2. All right, there's the whole thing if you need to freeze it and copy it down. How do we subtract? Again, common denominator, subtract the tops. You can multiply this 5 by 3, this 3 by 5. Now they'll both be a 15. Whatever I do to the bottom, I do to the top. I get 9 over 15 minus 5 over 15 equals 4 over 15. And then check to see if this can be simplified. In this case, it can't. All right, here's one for you. Might want to pause the video, try one on your own. All right, so I'll factor this. I'll take out an x, leaving behind an x minus 2. I'll factor this one, just take a 2 out, leaving behind an x minus 2. Well, they both have an x minus 2, so all I need to do is add in a 2 on this side and an x on this side, and now they have the same 3 factors. But I added a 2 to the bottom of this, so I'm going to need to add a 2 to the top of this, added an x to the bottom of this, so I'll need to add an x to the top of this. I will go ahead and just distribute on the top here. And now I only need one copy of the bottom. I might consolidate that 2 and that x to become a 2x, but I'm not going to distribute it in because I want to leave the bottom factored. And now I've got, when I distribute this in, I'll have a 2x plus 4 minus, when I distribute in this x, I'll have an x squared plus 2x. All right, this negative needs to get distributed. And when I do that, I'll have a negative 2x over here. Well, that can cancel out this 2x. And on top, what do I have? I have a 4 minus an x squared all over 2x times x minus 2. I'm going to take out a negative 1 from the top and rearrange this a little bit to make it negative 1 times x squared minus 4, because I took out a negative 1 from both of these to be able to write it in front, over 2x times x minus 2. And now that looks like I can factor it using conjugates again. Negative 1 times x plus 2 times x minus 2 all over 2x times x minus 2. And again, we see the situation where by factoring again, after combining, something else pops out that can be canceled. And now I'll go ahead and distribute that negative 1 back in. And I get negative x minus 2 all over 2x. So, these problems are often set up in a way that they will simplify way down. Just so you get lots of practice with factoring and stuff. All right. So leave it like that, or you could leave the -1 factor down. Either way is fine. All right. Complex fractions. So we can have fractions made out of fractions, and we can even put variables in there. The basic strategy when approaching these is combine any two fractions that are on one side of the bigger fraction. You see how this fraction line is much longer. And then we can copy dot flop. So just focus on the bottom. Don't let the size of this fraction freak you out. We're just going to combine the bottoms here. Got to get a common denominator, so I multiply by 2, I multiply by 3. Whatever I do to the bottom, I do to the top. And I get, we'll just leave a 1 over a up here, over 4 over 9, or not 9, 4 over 6, minus 27 over 6. And now the bottoms can be combined. So this can become 1 over a over negative 23 over 6. That's an a, kind of looks like a 9. Now we can copy dot flop. You copy dot flop over that bigger fraction line. So still copy dot flop. This time you copy the top of the fraction, 1 over a. Dot replaces that middle fraction line, then you flop the bottom. I'm going to keep the negative on top though. Rather just keep the top of my fractions always negative, and this equals -6 over 23a. And no more common factors, so we can put a box around that. All right, that's that for our lecture video here. I'll embed a few more questions, and have a good rest of your day.